I'm Richard West at Northeastern University. I had the honor of working with Bill Green as a postdoc from 2008 to 2011, roughly, yes. There's more about the history of RMG later on in this talk, so I'll recap some of that. Most of these slides are Bill's slides from 2 years ago at the workshop. My ambitious goals to change them faltered with lack of time and realizing that they were pretty good and that he put in a lot of good stuff. So, but I've got to kind of match his pace if I want to finish in half an hour. So bear with me as we go fast through some of this stuff. So the goal of RMG, right? What is the whole point? So the aim is to predict reactive chemistry of a given system automatically. So the emphasis is on predictive and automation, determining all of the relevant species and the reactions at the specified conditions, and then provide all of the numbers that you need in the simulation. So you've got to choose which reactions to include and then get all of the parameters. The goal is to reduce the huge amount of human effort that was needed for decades to build these models without a computer, and therefore make it more practical to build better models for things like combustion, reducing pollution, increasing fuel efficiency. So it started off being very good at pyrolysis and combustion. That's what it's had the most use for and is therefore what it's best at. But we keep on adding new features and trying it on new things. So it's now can be applied to other things like catalysis and liquid phase stuff and even polymers and things. So it's a predictive tool to construct these comprehensive models that are made up of elementary reactions. And then it estimates all of the unknown kinetics and thermodynamics. So this is showing the mechanism for the pyrolysis of JP10. And it's lots of, if you wanted to just describe how JP10 breaks down as a function of temperature, you could probably come up with some complex rate law and expression, but it would be very hard to then guess the parameters in that complex rate law. If you write down all of the elementary steps, it's very easy to guess the parameters because you say, well, it's a unimolecular reaction, it's first order. I can just write down mass action. I know that it's concentration. Or if it's a bimolecular, you know, it's the concentration of the two reactants multiplied together. So if you write down elementary reactions, it's much easier to guess the parameters. But the trouble is there's then thousands of elementary reactions. It's a large open source package. Active development, last time we added up, there was probably about 40 grad student years of effort had gone in, but I haven't added it up recently, so maybe it's 50 or 60 now, or maybe even more. I should do the maths again. But it's a lot of people working for many years now. There's also lots of other tools to help you build, solve, analyze kinetic models. Sensitivity analysis, uncertainty. There's lots of extra add-ons and tools that we kind of bundle with it because they all use part of it. It also has with it a lot of databases of the raw data that's needed and lots of methods to estimate the main parameters. So there's 3 main papers worth reading to get a good overview. The Gao paper was the first one about the Python version of RMG, 2016. The next major update was 5 years later, the Liu paper. It's kind of about the second release of RMG Pi. And then the third paper written here is mostly about the database and the parameter estimation methods. That focuses on how we come up with the parameters and where they're all stored. So why do we even need an automated mechanism generation? This is showing lots of different mechanisms to describe just combustion from a combustion paper. Liu and Law is now 15 years old, but showed the progression over the previous 30 years of models getting larger and larger and larger until we've now got thousands of species and tens of thousands of reactions in these kinetic models that are routinely being published. So as I was saying, if you can write elementary step reactions, it's then easy to write the rate laws. And you can do this by hand, and certainly these ones were done by hand, but it's getting harder and harder, and so you want to automate it. Sometimes there are so many reactions, it's impossible even with a computer to find them all. And that's one of the challenges we'll talk about in the next couple of days is how to pick which ones to include. So the ultimate goal, you'll be able to quickly, automatically construct a chemical mechanism for any system of your interest, and it will be accurate. So nearly any system, and the hope is that it's accurate. But that's the goal. A major challenge is which reactions to include in the model. So if you were to look at propene, is that right? Yes. Pyrolyzing or breaking down, you might come up with these reactions and think that, as a chemist, that that's probably a good description of what's happening. But there's lots of other stuff that also could be happening that you've chosen to ignore or said is probably unimportant. And even the grayed out bit is incomplete. You'll notice that this is a radical and therefore it won't stop there. That's going to react with everything else. And so, so there's a lot of stuff that we leave out of a model. So the computer, first of all, needs to be told everything that's possible. And we use these reaction templates. So you need an extensive set of reaction templates that will help the computer know everything that could happen. But then there's too many to include, and certainly too many to include with accurate numbers. So what people tend to do, and what we automate, is use a lower accuracy estimate of most of the parameters to make original decisions about what to include. And then say, OK, now I've included the things I think are most important. Analyze the model and find out which of those parameters really are important, and then go and calculate those more accurately. Now, there's an emphasis on important. We'll come back to this later in the day or tomorrow. Important depends on the reaction conditions that you're running at, the observables you care about, and your error tolerance. So if what you care about is the flame speed because you're trying to model a flame inhibitor, that could be important. If it's looking at the ignition delay because you're modeling a fuel, that's important. So what you care about matters. The conditions are crucial because at high temperature, the pathways could be different than at low temperature. Different pressures will change things as well. OK, so for every species, we need to know the thermochemistry, and for every reaction, we need to know the rates. So there's a lot of numbers that you need. RMG can estimate almost everything that you might need. So it's not only the thermochemistry, the enthalpies and entropies of every species, the rates of every reaction. It can also do solvent corrections and allow you to correct for solvents, vapor-liquid equilibria. It can estimate the pressure dependence of third-body gas phase reactions. It can estimate diffusivities. If you need to solve a flame, you need to know how fast the little molecules diffuse through air, etc. And so it's a lot of tools that are very useful. A lot of these estimates are not very accurate, but they're very fast. The emphasis or the kind of philosophy has always been some guess is better than nothing. It's better than leaving it out. And so we come up with things that are very fast, but there are so many parameters to guess that we need to make them quick. Obviously, we'd rather have high accuracy ones. Some can come from measurements. Most of the high accuracy ones now come from quantum chemistry. So for gas phase combustion, which is, as I said, where this largely grew from, for 5-10 years now, it's been true that you can calculate most things more accurately than you can measure them, if you're careful enough and trust your methods and computers. That's not yet true on catalysis and solvation and things, where we still rely on more experiments and fitting and stuff. But often the high accuracy number you want is not available, so you have to go off and calculate it. If you tell RMG that you have a good number that you trust, it will use it. Otherwise, it will estimate things. So get all of the good numbers you can and feed them into RMG, and that will help it along. So the whole concept relies on quantum chemistry because there aren't enough elementary reactions and individual species that have been measured experimentally. So this whole kind of idea of the original RMG in 2000 kind of launched because Bill's group was doing a lot of DFT calculations, more than most other groups at that time. And you'll know from like 1998, around 2000, this B3-lip functional for density functional became wildly popular. And but this is showing the inaccuracy. So we've got the error in kcals from active thermochemical tables from the ground truth is 0. So each of these ticks is about 2 kcal. So 2, 4, 6, 8. So this orange is just uncorrected B3-lip. You'll see that it's very bad. Has been widely used for decades. But the green group switched as soon as they could afford to using much more accurate things like CBS QB3 as the standard workhorse for many years. And you can see this is now kind of within 3 kcal, 2 kcal. if you add these bond additivity corrections, you can remove a lot of systematic error, and then you can end up with the blue error curve. So now this is what they call chemical accuracy, that you're kind of mostly within a kilocal. Even more expensive methods, these correlated ones are now more used, but these are getting fairly expensive. It depends on the size of your system whether you can afford to do these, but these are now routinely much more accurate. The big challenge is, or the big question is, how accurate is accurate enough? And that depends on temperature, because you want your errors to be less than gas constant times temperature, less than RT, which means that at lower temperatures, you need to be more accurate. And so this means that you will end up with a big error in your final results at low temperatures, because you can't afford to have a big error in your parameters. It also depends on the sensitivity. So some parameters are very sensitive to some systems are very sensitive to some parameters. Usually we're lucky that we're mostly error tolerant, that you can get some parameters wrong and the number you care about in your simulation won't be very wrong. But sometimes the systems are very sensitive to stuff. Okay, so how RMG works. You give it the inlet conditions and your composition. So what fuels you're putting in and the temperature and the pressure. And you give it your kinetics and thermodynamics libraries. This is an example of the current syntax for it, a big list of reactions and stuff. You then tell it the tolerances of what to include and how much to leave out, when to stop the simulation. So kind of, I want it to, or until 99% of my fuel is gone. And then you get a kinetic model, which you could then use in other software like Chemkin, Cantera, and reaction mechanisms. Sometimes there's confusion among people who don't do kinetic modeling about the difference between RMG and Chemkin, or I use Cantera to make a model, or I use Chemkin to make a model. No, they use Chemkin to simulate a model, which you generated in RMG. Now, inside of RMG, it has to run some simulations, so there's some coupling of this is kind of there's a distinction between making the model and simulating the model. So RMG kind of grows these mechanisms incrementally. So it's got this, you'll hear a lot about the core and the edge. So the core is where you start off with your fuel, so this is ethanol and oxygen. And then you say, okay, it's going to apply the templates and think of all the things that can be made by those two molecules reacting with each other. And then it runs the simulations at the conditions you care about, and it decides which things are important and need to be included. And then it will create some more, and then it will keep on iteratively moving stuff into the core, running simulations, generating more things on the edge. So in the end, you might end up with a core mechanism with dozens of species and hundreds of reactions, but the edge is often an order of magnitude more, at least. So when you see there's a model with 10,000 things in the core, there's probably 100,000 that it considered on the edge. So there's now about, what's the latest count, 80 or something, 60? Used to be 20 or so. We keep on adding new types or classes of reactions. The most common ones for combustion, things like hydrogen abstraction, radical recombination, adding to a double bond. It's kind of things you might look up in an organic chemistry textbook. And they're all written as general recipes that then apply these templates every time they can occur. How it chooses what to put into the core, there's now a number of mechanisms of ways to do that. They're all mostly based on the rate. So I kind of, as a category, I say it's a rate-based algorithms, rate-based decisions. The simplest to explain is this flux, that you just say which edge species have the highest flux, which ones are being made the quickest, put those into the core. That's the simplest to explain. It's not always the best, and we'll hear more later, I hope, about how to choose the others. A benefit of this, only the species that seem important are included. It's lasted a long time, using this method for decades now, without most people shifting to alternatives. Another benefit, you don't need to guess what's important in advance. You can just systematically tighten the tolerance and your model will get bigger and bigger and more inclusive. One disadvantage is that if your estimates are wrong, you'll add the wrong species and miss important stuff. So if the parameter estimate says that the rate is too low, you might then never include that in your core and then never discover it's important. It never shows up in your sensitivity. You never do the DFT. And so that's one hazard. that if you underestimate something or estimate its enthalpy is too high or estimate its rate is too low, you might never include it in your model. Another is that something that's made very slowly catalyzes something else later on and turns out to be really important. So there are cases where a low rate is crucial to get something else right. And so we'll hear more about the algorithms for species selection later. So basically, it's a black box. You put in a bunch of DFT calculations and you get your detailed kinetic models. And inside this black box, there's a lot of databases, rules, group additivity, ways to estimate things. And then we normally close the loop by doing more calculations based on the kinetic model and putting them back in. We'll hear more about that as well. When the numbers are missing, we've got to estimate things very quickly. The way we estimate thermochemistry is through Benson group additivities based from the 60s or something. You've got some complicated arbitrary molecule. You can break it up into functional groups, and then you've got far fewer possibilities of groups. So he was able to tabulate every time you've got a C double bond O connected in a ring, it's the same enthalpy, and so these two contribute the same, and if they're in some other molecule, they are the same. So you can then look up a much smaller table of functional groups and can estimate any arbitrary molecule. This idea we then apply to all sorts of other things, the way we estimate the solubility parameters, the diffusivities, all sorts of stuff use this kind of group contribution method. The kinetics is similar. We still focus on these kind of functional groups of what is near the reacting center, and we organize them in a decision tree. And so we might say, at the most general terms, I've got a double bond. And then we'll say more specifically, it's a carbon is one end of the double bond. And then you might say the other end is also a carbon. And then you might say this carbon's primary. And so you can get more and more specific as you go down the tree. And then you might have one for the radicals as well. And so this is how we estimate the rate rules. RMG has been applied to many things, getting gradually more complicated over the years as we keep on adding challenges for ourselves. But yeah, it's been used for a lot of stuff, and it works pretty well. RMG today. So the models built using RMG and then quantum chemistry calculations of the important rates and some rate estimates, they're now fairly predictive. You can actually predict things for combustion and pyrolysis and some other systems. You can build big models pretty quickly. There are still some limits on how big you can get. Far bigger than a human, but still not infinite. It's good for quickly seeing what's predicted with current knowledge of chemistry. Bill's point here was that if there's unknown chemistry, no one will have put that into RMG yet, and it will never discover it. So it's not really artificial intelligence. It's just like all the other AI these days. It's just quicker. It's speeding us up, but will never do better than us. The discrepancies motivate ongoing work. So when you find that it doesn't work, you then dig in to figure out why, and that's how we learn chemistry. Why aren't RMG models perfect? So there's two main types of error. There's the mechanism truncation error, which is that your model was too small, you left some reactions out. And then there's the parametric error of the parameters in your model were wrong. There's some coupling, as I mentioned. If your parameters are wrong, RMG might choose to leave the reaction out because of the way it does the rate-based expansion. And so this is the coupling we talk about. But when you're building a model, and we'll hear more about this from Matt later this afternoon, the strategies for getting a good model. Try to focus on getting some parameters fixed, the important ones, but then keep on iterating and going back and building the model again as you fix parameters, because the reactions that end up in the model could change as a result of your parameter fixes. So you need to kind of cycle around this loop, which I think we illustrate here. Yeah, so you'd start by, first of all, just run RMG, and you'll get your model. Then do some sensitivity and uncertainty analysis. So that means seeing which of the parameters in your model as it stands control the things you care about, and which ones are uncertain. So if you can figure out, okay, this one's important and unknown, go and calculate it, or look it up, or find it. Refine the model parameters. A lot of people would just say, okay, now I've got my finished model, and stop here. But it's much better to put those back into the RMG database and build a new model, because you might then discover new pathways, or it might change its mind about what to include. And so you should iterate this loop several times until it's kind of converged and stopped changing much. And then compare it to experiments and see how well you do. It's not the only mechanism generation software. The concept came around in the 70s when computers were coming to be used more widely, and everyone was like, what can we use these for? Some chemists said, hey, we could use these to build these models that are a pain to do by hand. Those ideas were good, but the actual implementations kind of died out. We came up with better ideas. There was kind of ways to represent things as matrices, and now we use graphs and so on. But it started in the 70s. By 1980, there were several groups that worked, but they're not being used anymore. In the 90s, better software came about. NetGen is, I think, the one that Bill worked on while he was in industry. And then when he left industry, came to academia, started at MIT, he had a student who was into computer science stuff and started writing the RMG in 2002 in Java. And Bill chose to make it an open source thing, and I think that was a fantastic decision that helped it grow, because most of these other things, other software packages that exist are not shared, and therefore don't have so many people contributing to, and never kept getting better at the same pace as RMG. I always chuckle about this. Designed for maintainability and extensibility with the RMG Java, but by 6 years later, when I arrived as a postdoc, it was neither maintainable nor extensible anymore. I don't blame Jing Song, who started it. I think she was probably a fine Java programmer, but the rest of the people contributing were not good Java programmers. And so it quickly became a spaghetti mess. Josh Allen and I said, okay, I hate Java anyway, let's try Python. It's quicker, easier for people to learn. Hopefully people won't mess it up as much when they're contributing. And so we rewrote the whole thing in Python. It took us a long time before it was on a par with the Java. We realized, oh gosh, this is a bigger project than we'd imagined. But eventually it kind of surpassed the Java one, and Java stopped being maintained in 2016, and it kind of, the Python one took over. So it's not alone, there are others, but it's the only kind of widely available open source one that everyone can contribute to, and it has some other benefits. Oh, wow, I went even faster than Bill. All right, what did I miss, or what should I talk more about?
Or we can take any questions.
Yes, question, exactly, that's kind of what I mean. Questions? Yes.
Approach.
Say more about the iterative approach. Yeah.
More about the iterative approach.
Yeah. So I should have stopped the sharing. Yeah. So I think we'll hear more from Josh Allen on advice for building mechanisms. Yeah. So when you first build a model, it's what it chose to put in depends on its estimates of the parameters as it's starting out. And so if you're putting a new fuel molecule in for the first time, it might be missing some of the important pathways. And so you've got to think then as a chemist, like, could something be missing, or are the parameters of these well enough known? So it's often good to say, okay, the very first few reactions, I'm going to run DFT or run quantum chemistry and then build the model. The sensitivity will tell you which of the parameters you have included are showing up as important. And anything that you've overestimated will show up as important because it's messing everything up, it's too fast. But the warning is anything that you've underestimated might not show up as important. And so there's a hazard here. You've got to also do some uncertainty analysis of like which of these are poorly known. But the idea is that if you keep on fixing the important stuff and then building the model again, it will gradually include the right things into the core. It's worth starting off your first few times with pretty loose like convergence parameters here. Build a smallish model until you fix the main like kinetic and thermo parameters. And gradually, as you make the quality of the parameters better, make the size of the model larger as well. Does anyone else have experience of building models with RMG? Contribute to that. Move on. Yeah.
I'm sorry, can I ask one quick question? Um, could you talk a little bit about like whether or not it's better to do lots of low level quantum chemistry calculations and try and like maximize the number of reactions that you're doing it for, or if it's better to kind of iterate and do higher level theory as you're identifying important reactions?
Great question. It makes me think of Sevi's work, which was she was trying to automate some of this whole process of have it automatically choose which reactions to focus on. And she found that it's important to consider not only the sensitivity of the parameter, like how does it change the thing you care about, your ignition delay, but also not just the uncertainty in the parameter, but how much you think you can decrease the uncertainty in the parameter. So if you're only going to do cheap quantum chemistry calculations that are in themselves fairly uncertain, you might not be gaining much versus doing a really expensive calculation, you might decrease the error more. But if the original guess was really bad, or you have reason to suspect it's really bad, then get it in the right ballpark. So it's tough to say as a general rule, but I would say try to get many things close enough and then focus on, then you can trust your sensitivity analysis more to tell you what really needs to be good. But yeah, if your numbers are too wrong, then your sensitivity analysis is not trustworthy. And so the whole kind of choosing what to focus on doesn't really work. So yeah, it's a little hard to give a perfect recipe, and it's a very good question.